Imagine a world of water, hidden beneath ice. The universe has hidden oceans in unexpected places, as small icy moons. These ocean worlds have changed our search for life. A moon encased in ice, hiding a liquid ocean larger than Earth's. Water, essential for life, is everywhere. If the water is there, could life be there too? What if all life needs is water, energy, and the right building blocks? These ocean worlds might have all three. We are sending new missions to get a closer look. We stand on the precipice of a discovery that could change everything. We are looking for our neighbors in the deep oceans of our solar system. There is a deep fascination with the unknown. It drove our ancestors to cross continents and sail uncharted seas. Nothing captures our imagination like a hidden ocean. Locked away beneath a world of ice, it speaks to our curiosity. Among the many worlds, Europa and Enceladus have emerged. Our robotic emissaries have shown us that these are not dead worlds. Their frozen surfaces conceal vibrant, watery interiors. They are worlds of possibility, a new frontier in our search for life. Europa and Enceladus offer a potentially habitable present. We find ourselves at the beginning of a new chapter in our cosmic story. We are ocean explorers once again, but this time the seas are not on Earth. Our story begins with a small, unassuming moon. This is Enceladus, one of Saturn's satellites. When the Voyager spacecraft flew past, they sent back images of a bright, smooth surface. It looked like a world that was geologically dead. When the Cassini spacecraft arrived, it was equipped with more sensitive instruments. It turned its gaze towards tiny Enceladus. What they found was not a dead world at all. Instead, they discovered a place of startling complexity and activity. Cassini detected a strange, wispy atmosphere around Enceladus. It was as if this tiny moon was somehow feeding the ring. It was an active world, venting material into space around it. This completely changed the scientific perception of Enceladus. The only way to find out was to get even closer. What they would find would astound the world. As Cassini approached Enceladus, its cameras revealed something extraordinary at the moon's south pole. A bizarre landscape of long, parallel fractures etched into the ice, known as the tiger stripes. These geological wounds radiated an incredible amount of heat, suggesting Enceladus was not frozen solid. Tidal heating was the prime suspect, generating warmth to melt ice. What if Enceladus had a subterranean ocean with the tiger stripes acting as vents, allowing material from that hidden ocean to escape into space? Cassini would fly directly through the plume to sample its composition. Was it just ice vapor or salty water blasted from a vast hidden ocean? The stage was set for one of Cassini's most dramatic encounters. The moment of truth arrived. With pinpoint precision, the Cassini spacecraft plunged through the faint icy mist erupting from the south pole of Enceladus. Its instruments were on, gathering data, analyzing every particle that struck them. It was a journey through a cosmic geyser. The spacecraft was not just seeing the plumes, it was flying right through them, becoming part of the phenomenon it was studying. This was robotic exploration at its most intimate and daring. For a few tense minutes, Cassini became an extension of our own senses, reaching out across hundreds of millions of kilometers to touch and to taste another world. The data it sent back was nothing short of revolutionary. The analysis was conclusive. The plumes were not made of pure water ice. Cassini's instruments detected simple organic compounds, molecules containing carbon, which are the fundamental building blocks of life as we know it. They also found salts, like those found in Earth's oceans. The presence of salt was a critical piece of evidence. It strongly implied that the water vapor had been in contact with a rocky core deep beneath the ice, dissolving minerals into it over a vast period. This was not just melting ice. This was a sign of a large, stable body of liquid water, a true subterranean sea that had been interacting with rock. But the most astonishing discovery was yet to come. On one of its final, deepest dives through the plumes, Cassini detected molecular hydrogen. This was a blockbuster finding. On Earth, molecular hydrogen is produced in deep-sea hydrothermal vents, where hot, mineral-rich water from the planet's interior reacts with rock on the seafloor. These vents are oases for life, providing both the chemical energy and the nutrients needed for entire ecosystems to thrive in total darkness. Finding molecular hydrogen erupting from Enceladus was the strongest evidence yet that similar hydrothermal vents could exist on the floor of its hidden ocean right now. The pieces of the puzzle had all fallen into place. The tiger stripes, the heat, the geysers, the salt, the organic molecules, and the hydrogen all pointed to one inescapable conclusion. Enceladus, the tiny bright moon of Saturn, possesses a global liquid water ocean beneath its icy shell. And at the bottom of that dark ocean, there are likely hydrothermal vents, providing a source of chemical energy. It has water, it has chemistry, and it has an energy source. These are the three key ingredients for life. A world we once dismissed as a frozen dead ball of ice had suddenly become one of the most promising places in the universe to search for life beyond Earth. Our journey now brings us to Jupiter, the king of planets, and its enigmatic moon, Europa. Europa is about the size of Earth's moon, but its surface is strikingly smooth and bright, laced with reddish-brown lines. Unlike most moons, Europa's surface is almost free of craters, evidence that it's constantly renewed. This smoothness hints at a dynamic world, with something beneath the ice erasing the scars of impacts. Long before we saw Enceladus's geysers, Europa was the first place we imagined a hidden ocean far from the sun. The Galileo spacecraft, arriving in 1995, revealed Europa's surface in stunning detail, a frozen jigsaw of ridges and cracks. These patterns resemble Earth's sea ice, suggesting Europa's crust floats atop something more fluid. The fractured landscape points to powerful forces at work, vast slabs of ice shifting and refreezing. Scientists saw clear signs of motion, as if the surface was being broken apart and healed again and again. The resemblance to Earth's polar ice flows was uncanny, strengthening the case for a subsurface ocean. Europa's icy shell appears to be a thin veneer, floating on a vast hidden sea. All evidence pointed to a colossal ocean beneath the ice, possibly twice the volume of all Earth's oceans. Europa became the original poster child for ocean worlds, a place where life might find a way. Let's zoom in on Europa's surface, a world etched with endless lines called lineae. These aren't just cracks, they're immense features, some stretching thousands of kilometers. Double ridges, dark bands, and chaos terrains reveal a history of relentless stress and upheaval. Jupiter's gravity flexes Europa, cracking the ice and creating these scars. The moon's surface is a record of constant motion, not a frozen wasteland. In chaos terrains, the crust shatters and refreezes, hinting at slushy water or warm ice just below. These features are powerful evidence that liquid water or soft ice lies close to the surface. The dynamic boundary between ice and ocean is written in every fracture and jumbled block. Above, the vacuum of space. Below, a dark, global ocean. Europa's surface is a geological storybook, each feature a clue to the ocean beneath. The ice is moving, breaking, and floating on a sea that may be over 100 kilometers deep. Europa's ocean could hold more water than all of Earth's combined. To confirm Europa's ocean, scientists needed more than surface clues. Galileo's magnetometer provided the breakthrough. As Europa moved through Jupiter's magnetic field, Galileo detected a secondary field, generated from within Europa. Europa is too small for a molten core, so what was conducting electricity? The answer, a global ocean of salty water beneath the ice. This ocean acts like a giant electrical coil, responding to Jupiter's magnetic field. The data made the hidden ocean a near certainty. It was like hearing a hollow echo, proof of a vast space below. The ocean is not just real, but salty, suggesting contact with a rocky seafloor. Over time, minerals dissolve into the water, enriching it with the ingredients for life. Europa now had all the essentials: liquid water, energy from tidal heating, and a rich chemical environment. The case for a habitable ocean world was stronger than ever. The search for life had a new, promising target. For years, Europa's ocean was only inferred, until hints of plumes emerged. The Hubble Space Telescope detected faint water vapor above Europa's South Pole in 2013. These plumes, if real, would be taller than Mount Everest, erupting from the hidden sea. Later observations suggested these eruptions might be sporadic but genuine. Plumes would allow us to sample Europa's ocean without drilling, just by flying through the spray. This could reveal salts, organics, even possible biomarkers. The discovery re-energized Europa exploration, offering a shortcut to its secrets. Europa and Enceladus now both beckon as ocean worlds venting their mysteries into space. Enceladus is small and active. Europa, larger and more reserved, but both are tantalizing. Each has water, nutrients, and energy, prime ingredients for life. The question is no longer if there's an ocean, but what's inside it. The search for life beyond Earth is more exciting than ever. Europa and Enceladus, two icy moons, two hidden oceans orbiting distant giants. Both are natural laboratories for astrobiology, with stable, long-lived seas beneath protective ice. Tidal heating keeps their oceans liquid and stirs geological activity. On Enceladus, it powers geysers. On Europa, it cracks the crust and may warm the ocean below. Both oceans likely touch a rocky seafloor, allowing minerals and nutrients to mix in. This rock-water interface could host hydrothermal vents, potential oases for life. Each world has water, chemistry, and energy, the classic recipe for habitability. Yet, they're not twins. Europa is vast and deep, Enceladus small but hyperactive. Their differences offer unique opportunities and challenges for exploration. Together, they show that ocean worlds may be common, not rare, in the universe. The search for life is no longer science fiction, it's a real, unfolding quest. The next chapter in our exploration of the cosmos is just beginning. Enceladus blasts its ocean into space through its tiger-stripe fissures. The Cassini mission proved that we can fly through these plumes and taste the ocean directly. Europa, on the other hand, plays its cards much closer to its chest. Its icy shell is thought to be much thicker. This makes accessing its ocean a monumental engineering challenge. Europa's immense sea, in contact with its rocky mantle for billions of years, might be incredibly salty. Enceladus's ocean is likely much younger, its chemistry simpler, but incredibly dynamic due to hydrothermal activity. The hydrogen Cassini found suggests a powerful chemical disequilibrium. Europa's total tidal energy input is much greater than that of Enceladus, creating a concentrated oasis of habitability. If you were a cosmic gambler, where would you bet in the search for extraterrestrial life? Enceladus, with its accessible plumes, or Europa, with its vast ocean? Both are top priorities for exploration, offering unique insights into habitable worlds. Enceladus is appealing due to its accessibility and active hydrothermal chemistry, potentially harboring life. Europa's appeal lies in its scale and stability, with an ancient ocean that could have fostered life. The challenge is its thick ice shell. These moons aren't competitors but collaborators. They are independent experiments in planetary habitability. The coming decades promise thrilling discoveries. How do you look for life on a world you cannot visit? We must be clever cosmic detectives, searching for clues from millions of kilometers away. We are not looking for aliens or fossils, but for something more fundamental. We are searching for the chemical fingerprints that life leaves behind. Biosignatures. On Earth, life has profoundly altered our planet's chemistry. So when we send a probe to taste the plumes, we are looking for a specific pattern. Are there complex organic molecules? The key is context. The goal is to find a pattern so unusual it defies a non-living explanation. This is the meticulous work of astrobiology. It is a science of probability and deduction. Only then can we know what to look for, what would be truly anomalous. It is a painstaking process of eliminating all other possibilities. The era of preliminary reconnaissance is over. The Voyager flybys gave us our first glimpse. The Galileo and Cassini missions gave us the stunning revelation of hidden oceans. Now we are entering a new phase of exploration. We are no longer asking if these worlds are interesting. We know they are. We are now building and launching a new generation of robotic emissaries, spacecraft designed specifically to answer the profound questions that the previous missions have raised. These are not general-purpose explorers. They are focused, specialized machines, armed with instruments tailored to the search for habitable conditions and the fingerprints of life. The great search has begun in earnest. Leading the charge is NASA's Europa Clipper mission. This magnificent spacecraft, which launched in 2024, is now on its long journey to the Jupiter system. It is not a lander, nor will it go into orbit around Europa itself. Orbiting Europa would expose the spacecraft to the ferocious radiation belts of Jupiter, which would quickly fry its electronics. Instead, Clipper will perform a clever dance. It will orbit Jupiter and make dozens of close, daring flybys of Europa, some as low as 25 kilometers above the ice. During each high-speed pass, its suite of 9 advanced instruments will map the surface, analyze its composition, and search for those elusive water plumes. Clipper's mission is to characterize Europa as a habitable world. It carries powerful ice-penetrating radar, which will act like a geophysical sonar, mapping the thickness of the ice shell and confirming the depth and saltiness of the ocean below. It will have high-resolution cameras to scout for future landing sites. Crucially, It will have mass spectrometers and dust analyzers, instruments designed to taste any material ejected from the surface. If Clipper is lucky enough to fly through a plume, it will be able to analyze its chemical makeup with unprecedented sensitivity, searching for those key organic molecules that could hint at the presence of life in the ocean far below. But the ambition does not stop there. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, is also en route to the Jovian system. While its primary focus is Jupiter's largest moon, Ganymede, it will also perform 2 crucial flybys of Europa. Its instruments will complement Clipper's, providing another set of data points, another look at this enigmatic world. Together, these missions will transform our understanding of Europa from a fuzzy picture into a high-definition movie. They will pave the way for the next logical step, a lander. A mission that will put scientific instruments directly onto that strange, frozen surface for the first time in history. Flying past a world is one thing, landing on it is another. A future Europa lander represents the next great leap in our exploration of these ocean worlds. It would involve sending a robotic probe to touch down on Europa's surface, a place with no atmosphere, bombarded by radiation and extreme cold. This lander would be a marvel of engineering, a self-contained robotic chemist. Its goal would be to sample the ice and analyze it directly. Material from the ocean is likely mixed into the surface ice. The lander would scoop up samples of this ice and feed it into a suite of sophisticated instruments. And what about Enceladus? Imagine a spacecraft that flies through the Plumes, captures the icy particles, and then flies all the way back to Earth, delivering a pristine sample of another world's ocean to our most advanced laboratories. This is the future of our search for life. We stand at a remarkable moment, on the verge of answering a question that has haunted us. Are we alone? Now, it has become a tangible scientific quest. The discovery of hidden oceans on Europa and Enceladus has transformed this quest. We have identified the prime suspects and dispatched our robotic detectives. Now we await the verdict. If future missions detect the chemical fingerprints of life, it would represent the single most profound discovery in the history of science. It would mean that the spark of life is not unique to our world. And what if we find nothing? A negative result would be just as profound. It would make the existence of life on Earth seem even more precious. Either outcome will forever change our perspective of our place in the cosmos, ready to learn the truth. The exploration of Europa and Enceladus is a testament to the insatiable curiosity that defines our species. The oceans of these distant moons are our new uncharted seas, a frontier not of geography, but of knowledge. To explore them is to push the boundaries of what is possible and to expand the scope of our cosmic awareness. Science is not a collection of facts, but a process of discovery. The story of these ocean worlds is a perfect example. This is a journey without a final destination. The pursuit of knowledge is an endless voyage that connects us to the cosmos, to each other, and to our future. We are building a legacy of curiosity. These small moons have taught us that even the most unassuming worlds can hide the most magnificent secrets, and to never, ever stop exploring. Because out there, in the vast, silent darkness, the universe is waiting to be discovered.